right. Edmund, can you please just tell me whether you can hear me very well, loud and clear?
From my perspective, it is fine. Yeah, we can see
Perfect.
also your slides.
All right. Well, hi everyone. My name is Shailen Sobi. I am, well, previously an AI solutions engineer. Since the 1st of February, I moved to a different role, which is an HPC software architect for Exascale. And I would actually like to tell you guys, maybe if you wish, note my email address, because I know a lot of people from the EuroCC group or consortium will be working with Exascale systems in the near future. So I would like to be potentially a point of contact, someone who can easily support you in your software development. Although today I'll be wearing my AI cap and talking about my previous role as an AI solutions engineer. That being said, there's a slide here that is by default. I need to show this, but I'll skip that. And the agenda for today will be the AI software stack for XPUs. And then I'll start talking about the oneAPI AI Analytics Toolkit. And then I'll show you all the various oneAPI tools in the field of machine learning and deep learning. Now, that being said, I'm also joined by my colleague, Vladimir Kilyasov. He's all the way down on the participation list. So he's going to monitor the chat for questions because I may not be seeing the chat while I speak. All right. That being said, this is like the big picture, big summary of 99% of the tools that Intel is providing in the AI space. You may feel that you are on top. You're either a data science engineer and you're working along this workflow, this pipeline. You're engineering data, then you're creating machine learning and deep learning models. Eventually, you want to deploy. So all the way down, there are a lot of tools and performance libraries and also side software components that Intel is putting a lot of effort and energy in creating a very useful ecosystem so that you can develop AI solutions with ease and also with satisfactory performance. Now, the rest of the talk, I'll be focusing on the oneAPI AI Analytics Toolkit that comprises of a bunch of these tools that are here where my mouse is moving. I'm not sure if you see it. Let me maybe use the pointer. There you can see. I'll be talking about TensorFlow and PyTorch in the deep learning section. For machine learning, I'll be talking about Modin, Pandas, scikit-learn, and then I'll focus also on OneDAL and OneDNN. Now, there are those software solutions like DevCloud. This was introduced early in the morning by my colleague Heinrich or Klaus Dieter. One container repository. This is something you can easily Google by typing Intel one container. There are a bunch of container solutions with pre-made libraries and all the software components all in one place you can easily use. And essentially, with this whole software stack, you can develop anywhere, be it a laptop, be it a workstation, be it in the cloud, or on an IoT based or edge solution. It doesn't matter. It doesn't matter where you are. It doesn't matter also what kind of hardware you have, be it a CPU, be it a GPU, be it a specialized hardware like an FPGA. This is the main idea that Intel has over the last few years developed and pushing forward is this openness. The idea where you can use anything to develop anything that you want. And I think that being said, there's a lot of potential to be able to develop high quality AI solutions, not only AI, maybe also HPC solutions using all the open tools out there. Now, the oneAPI AI Analytics Toolkit is it's a suite of AI tools bundled in a very nice package. You can just simply download the one toolkit, and you have all the optimized tools that you're already used to using, and it's out of the box optimized for all sorts of Intel architectures, and the performance libraries are bundled in there, and it's really easy to use. What is included in there? You have the Intel optimization for TensorFlow, or TensorFlow basically, PyTorch. There's also IPEX, the Intel extension for PyTorch. There's Model Zoo for Intel architecture, the Intel neural compressor for quantizing models, quantizing basically using 13.32 models and converting and doing inferencing in int8, for instance. This is what the INC tool does in a nutshell. Although I won't spend too much time, this was just a summary for you. And then in the machine learning space, the Intel extension for scikit-learn, XGBoost, all these two are powered by oneDAL, which my colleague Gennady before me presented. And then we have the Intel distribution of modding powered by the OmniSci backend. So that's for data analytics. Right, so I know that most of the people, maybe 99% of people doing AI, basically they use Python. Now the idea with Python is that there must be a way to accelerate Python. Python in itself wasn't meant for high performance. You may know that. And there is, for instance, the global interpreter lock in there that makes Python kind of single-threaded and has a lot of overhead with abstractions. There are no advanced data types. So in order to make Python efficient, we leverage performance libraries or mathematical packages like NumPy. So if you use NumPy, right away you can see some great performance. Now, in order to get even better performance, you would offload mathematical computations to performance libraries. Like oneMKL, for instance, introduced by Gennady earlier, is a highly optimized mathematical library that has all sorts of primitives, some even coded in assembly, just to show you how, to make the best of the hardware features. And that's how we are able to get really high performance with such libraries. Now, oneMKL is one example. oneDAL and oneDNN do the same. So the idea is that we need to escape Python as fast as we can and operate all our heavy lifting computations in those libraries. So this is what we basically do when we provide you this AI toolkit. All the high-level frameworks that you will use, let's say scikit-learn or TensorFlow, we immediately, as fast as we can, go into those performance libraries and do all the heavy lifting computations in those libraries. A quick intro to oneDAL. For the long version is oneAPI Data Acceleration Library. And essentially, this oneDAL, the interface is part of the oneAPI specification. So it's open, it's standardized, and it has Python bindings, Java bindings as well. And so it's just not a library. It's more than that. It has support for CPUs, GPUs, and in oneDAL, you have all the famous algorithms that you would use in machine learning, for instance. They're all implemented in there, and it's already integrated in scikit-learn as well as XGBoost. What is planned in the future is integration in Spark ML. There's interoperability with NumPy and Pandas. We'll have a talk a little bit later on the Pandas part. And it's already leveraging oneCCL for distributed communication. oneCCL is short for Collective Communications Library, also a very optimized library from Intel for distributed communication. oneTBB, oneMKL, and then leveraging the runtimes. So DPC plus runtime, commonly known as level 0. This is for accessing the GPUs, the discrete GPUs from Intel. That's for the future. And now, what is key here is that the API, it's designed to be hardware as well as vendor independent. And that's key. That's key to our mission of having an open ecosystem, essentially a cross-architecture open ecosystem. And this oneDAL interface, being hardware and vendor independent, answers this mission. Now, what is in oneDAL? Gennady showed that earlier. I just have this here for completeness of this presentation, but I'm going to skip that because you've seen that earlier. When you get the slides as well in PDF format, you will have this handy for consultation. That's data transformation and analysis. For machine learning, you have the very common algorithms already implemented and ready to use. They are also out of the box, highly optimized. Now you may ask, right, what actually makes oneDAL faster? There are so many things that Intel has done in order to make this performance library really fast. Out of the box, it has the best performance on Intel architectures, and that's leveraging oneMKL, right? So oneMKL versus other implementations like BLAS and LAPACK, MKL does better, right? Then it's able to leverage its inbuilt threading mechanisms to scale very well on multiple cores on a Xeon processor, for instance. And then when it comes to vectorization, it's able to look at the hardware and see, oh, okay, I have AVX512, for instance, I will use AVX512, hence giving you better performance. Then on top, there are better memory optimizations that oneDAL is able to use effectively and efficiently, hence giving you better performance. And also, before even the hardware is launched, we on the software side, we're already doing the work, the pre-work, to support future hardware. Like an example of future hardware would be a discrete GPU. The performance optimizations are already being put in place, meaning that if tomorrow, the moment you get a discrete GPU, your software, without changing much, already has the support for that hardware. And finally, scaling out opportunities. We will see how DAL scales very well on multiple distributed systems. I have a small example where I'm using K-means, I'm distributing on multiple machines. So using MPI, oneDAL is able to get best performance with scaling out. So that being said, let's have a look at scikit-learn. If you're in machine learning, 100% sure that you're using scikit-learn a lot. Now, we are putting effort in optimizing the tools that are out there in the open source world, but we also need to make sure that we're not changing things too much, that we're not changing APIs, making it hard for you to say, oh, now I want to get best performance, I need to change my code a lot. No. So the idea here is that we are able to give you the best performance without major code change. Most of the time, it's just importing a library and done. One example here is the Intel extension for scikit-learn. If this would be like the common scikit-learn example where you're loading a data set and then you're feeding, basically kind of the training, quote unquote, and then doing prediction. So to get better performance, all you have to do is from scikit-learn X. So that's the name of the package for Intel extension for scikit-learn. All you have to do is import patch sklearn and call it. That's it. The code here remains the same. So this is what we are saying by the same code, same behavior, but better performance. You'll see I have some performance graphs in my next slide to show you some examples. So the idea here is that it is scikit-learn in itself. We're not changing the API, so it is not like scikit-learn, but it is scikit-learn. And we are conforming with the standards. Nothing is being changed. The APIs are not being changed. I have here also some quick example. Either you call it in your code by doing that as an example here, or you can also do global patching like Python sklearn x glob patch sklearn. So this will do global patching across the board, meaning you don't even have to change your code individually, which is great. Let's have a look at some performance results. So here is a graph of speed up, right? So one would be the original scikit-learn, and the rest, the results here, is compared to level 1 here for Intel extension for scikit-learn. Across the board for various algorithms and data sizes, we can see that performance is higher. In some cases, for instance, with nearest neighbors of this data size, the performance speed up was close to 160x, and this is amazing. So this is a value proposition for you. You just get the AI toolkit, use the Intel extension for scikit-learn, and get better performance out of the box, right? Let's have a look at, so this was inferencing. Let's have a look at training, also getting better performance across the board. Here an example, 250x performance speed up. And for me, this is amazing. Now, here I'm comparing on the same hardware, the same software, and stock versus Intel extension for scikit-learn. Let's have a look at running that code on competitive hardware. The details of the competitive hardware is down below, but you can see that we did those tests, and the Intel extension for scikit-learn performed better than on competition hardware, and even on NVIDIA V100. So one would be Intel here, one, and everything was just below. So that's also a key point here, that for some workloads, optimized libraries do give you better performance on Intel. Now, that was oneDAL, right? And scikit-learn with this API compatible part. We also implemented a Python interface to oneDAL, and it's called DAL4Py. Now, you may say, oh, oneDAL is just with one A, and DAL here has two A's. So that's actually the old name of DAL. It was called Data Analytics and Acceleration Library. It's now just called oneDAL for Data Analytics Library. We did not change the package name because that would break the legacy codes, so we just kept it that way. So you may want to use it directly for scaling on multiple nodes. So here you have direct support for MPI, for instance, or in cases where you have streaming data, or maybe even gradient boosting. Talking of gradient boosting, let's have a look at XGBoost, for instance. I'm pretty sure if you do gradient boosting, you are using XGBoost. So for XGBoost, we also are able to highly accelerate gradient boosting with DAL4Py, and that also with very minimal code changes. Here an example where we are getting close to 23x performance boost by using DAL4Py. All right, so this is like the stock XGBoost and XGBoost with DAL4Py. So the code looks very simple. You're importing DAL4Py, so that's like the interface to oneDAL, right? Import DAL4Py, and then all you have to do is get gradient boosting model, and you pass that XGB model that you had before. So this is from your original code. You just do that, and then classification, prediction, whatever parameters, and compute. So that very simple piece of code just out of the box gave us 23x performance boosts. And you would see such performance boosts for your generic XGBoost code. So if you have not used DAL4Py so far, I highly recommend to go out and check it out. And if you don't get the performance boost, write me an email. I'm sure you have noted my email already earlier. So if you don't get the performance boost, I'll try my best to get the engineering team to look at your issue and find out why we're not getting performance. Now, that was performance, right? Runtime. When it comes to accuracy as well, there's almost / no accuracy loss at all compared with the two cases, XGBoost and XGBoost with DAL4Pi. All right. So that being said, let's move on to other areas where you would want to use DAL4Pi. So the classic mode of using that you would notice or encounter is batch processing, where data is coming in batches and you're processing them. Then there's distributed processing. So this is where you have data coming from multiple nodes, and then you're processing the data on a central node, and then online processing, that's AKA also known as streaming. So you would want to use DAL4Pi when you have cases like this. Let's have a look at distributed processing as an example. Here is a typical code, k-means, and we would like to use more machines. So all you have to do is just pass distributed equal true to the k-means method. Of course, DAL4Pi has been loaded before. And with just having distributed true, all you have to do is npi run to launch this piece of k-means code on 4 nodes, as an example here, -n4, and it's going to do this dense k-means algorithm on 4 nodes. So that's an example where you would use DAL4Pi. Now, let's look at some performance. Here, we used k-means distributed, and we have scaled on 56 cores. And you can see the performance benefit, right? So running this on 1 core and scaling it on 56 cores, the performance, like, just do the math, is like 50x plus, right? So this is speaking for itself. So that was oneDAL and k-means. Let's have a look at another tool in the oneAPI AI Analytics Toolkit, and that's called Modin, or its long version, Intel distribution of Modin. Now, currently, when you are doing machine learning and you are working with large data sets, right, you may be leveraging pandas, for instance, right, for processing large data frames. Now, the issue here is that after a certain data size, there needs to be a change in your API to handle more data, just because pandas is not efficient, pandas is not scalable. The good thing with pandas is that it's easy to use, but it's difficult to scale. So when you reach that kind of sweet point of 100 megabytes, usually you would want to look at other solutions that that scale better. So Apache Spark is an example that would scale better. The problem is it's quite hard to use Apache Spark, right? It would be nice if we had a tool that would be easy to use and easy to scale. The good news is there is this tool, and that's Modin. And it's super easy also to use Modin. All you have to do is import modin.pandas as PD, and that's it, right? If you don't believe me, let's have a look at a piece of code, actually in the next slide. But before, so let's have a look at Modin under the hood. Previously, if you have pandas, it doesn't scale, right? It usually uses one CPU. But a Modin data frame scales on multiple CPUs. So that's how it is able to get better performance. Now, this is just one thing. Modin is just not a pandas replacement. It has more than just that. It has support for SQL. It has support also for this DSL query language as well. And furthermore, it has support for the OmniSci data frame backend. On top of that, it also has native support for MPI. That's if you're using multiple nodes, right? So it's just not pandas replacement, but the whole suite of multiple benefits as well. Now let's have a look at a piece of code where Modin is in use. I told you it was just one line of code change, right? It's actually just this one. I'm replacing import pandas as PD. I'm doing import modin.pandas as PD. The code remained the same. I did not touch that part. And here, out of the box, I got 10, close to 11x speed up just doing that. So this graph speaks for itself as well. Let's have a look at a more real-world scenario, the NYC taxi workload. So here we're comparing pandas and Modin and the OmniSci backend. So here as well, the speed up, this is 1 for pandas, and the speed up is 9, 16 or 18 here. So basically it's more than 5x across the board, right? And if you would combine Modin, XGBoost, let's have a look rather at an end-to-end workload. So Plastic, for instance, is a fairly popular workload. Maybe you've come across it. It's for astronomical time series analysis. It does object classification. So for this Plastic workload, here's an end-to-end example where you were reading data. So read CSV, that's a big chunk of this pie chart. And then there's a lot of machine learning and this ETL extraction, transform and loading. So it's kind of jargon for data processing, right? So for this end-to-end example, when we are plugging in Intel optimized software tools, we're getting in total 18x better performance. And that's on one hand, minimal code changes, 2, just using the tools from the AI Analytics Toolkit. And 3, minimal amount of work, right? So it's linked to point 1, minimal code changes. So yeah, if you're not doing that, I highly recommend that you guys start looking at it. Do I have any questions so far in the chat, or maybe unmute yourself and ask before I move to deep learning tools? Okay.
Yeah, we don't have any questions for now.
Thanks, Vladimir. All right, so let's have a look at accelerating deep learning with the Intel oneAPI AI Analytics Toolkit. So in there, I'll be focusing on TensorFlow and PyTorch. And let's have a look at how these popular frameworks are being optimized with oneDNN. So oneDNN is short for oneAPI Deep Neural Network Library. And out of the box, the mission is aligning with our oneAPI initiative, right? The key message there is that it's open and it's cross-platform. Now, being open, I want to also stress here that oneDNN is open source. You can go on GitHub, look at the code. You can, if you see areas of improvement as well, if you're a nerd, right? You can do some optimizations by yourself and even request to have PRs, and we will have a look at it. So it's open source, it's cross-platform. And what is also key, and I've put it in blue here, is that the API for oneDNN is the same for Intel CPUs and GPUs. And this is key here because we are promising this, this idea that you will have your code on top, and that code is able to run on CPUs and GPUs without code change, right? And this is possible because the APIs are the same. And oneDNN has all the tools and technology to run best on CPU as well as GPU. We'll have a look at when we'll have a look at the oneDNN architecture. You'll see how that works. So the key idea is that it's abstracting the instruction set and other complexities, making it easy for you to leverage deep learning frameworks on top like TensorFlow and PyTorch. It runs on Linux, Windows, Mac OS. These are basically the popular OSs out there. And be my guest to have a look and even contribute if you wish. This is the GitHub link. The basic info for you is that the APIs on top is C, C++, and as well as SQL. We had 3 hours of presentation by my colleague Igor on that one. And for training and inference, we support all the popular data types out there, FP32, bfloat16, and for inferencing, also the quantized data types. And running on CPUs as well as GPUs. Now, I have to say that what is missing here, and that's the XE line. So here, these are integrated graphic GPUs, but upcoming soon will be our discrete GPUs. So the code name is Intel XE. So there is support as well for this there. And the mathematical primitives, you will come across these whenever you're doing some basic TensorFlow. These are the very common primitives that come into play. And what oneDNN does is make sure that these primitives run really fast. Let's have a look how that works in TensorFlow. Very briefly, of course, based on the timing. But I want to give you an idea what we have done under the hood. So when it comes to TensorFlow, there are kind of 3 areas of optimizations where we can get better performance. We can optimize on the operators, those mathematical operators, basically. We can optimize on the graph, because TensorFlow is a graph, right? And we can also do system-level optimizations, like optimizing on threading, optimizing on scaling on multiple CPUs, optimizing on scaling on multiple nodes as well. So oneDNN is able to do optimizations in all these 3 areas, and most of the case automatically. So I do have a benchmark, but I will go through this real quick. So here I'm comparing Intel optimized TensorFlow versus stock TensorFlow. Actually, the version that I'm comparing here is TensorFlow 2.5.0, which, by the way, already has oneDNN integrated, but it's not enabled by default. So what I've done in this script is I've run that script with TensorFlow 2.5.0 with oneDNN disabled, and running that script again with oneDNN enabled, and I'm comparing performance, right? So this is what I mean by stock versus Intel optimized, right? So that piece of code is very simple. It's just loading a topology from the model zoo. I think I'm loading a ResNet 50, and then I'm doing inferencing to get the throughput, right? So for the benefit of time, I will just go fairly fast for it, and also I'll increase the size. So I'm loading ResNet 50, and I'm doing inferencing in FP32. This is what I've done by picking index 0 here. And then I'm proceeding with loading the code and then doing any inferencing, right? So this is what this code does, essentially. Here I'm running the benchmark. And what is key here is at the end of the benchmark, when it's running, I'll scroll all the way down. It will give me the throughput here, 242,554 images per second. That's on the second run with oneDNN. So I told you I ran this before, and I've collected that performance number, which I've saved, and then I load it in memory, and then draw this this graph here. So this matplotlib graph here is basically showing the difference in throughput between stock TensorFlow 2.5.0 and TensorFlow 2.5.0 with oneDNN enabled. You can see that the throughput is higher, so higher is better, and the speed up basically, so this graph in speed up mode is 2.3x faster. So without changing the code, the Python code itself, just kind of switching the 2 binaries, even not quite, it's just enabling a system variable to say 1DNN is enabled. Just doing that, I got 2.36x performance boost. And all of this is coming from 1DNN. Now, what actually is in 1DNN that is doing that? So in brief, there are operator optimizations. For instance, a simple case like this where you have input tensors and then you're passing it to a mathematical operator like matmul and then doing an add. What is going behind the scene is that 1DNN is going to replace this matmul with the 1DNN optimized version of matmul and running this faster. That's an example. There are a bunch of these, so convolution, backspooling, batch norm, and so on, and concatenation. So all of these, so forward propagation and backward propagation, all these common primitives, they are highly optimized in 1DNN. If you want to obviously have more information, you can go directly on the GitHub. You can even look at the code, the implementation of these, if you're curious. Now, these are operator optimizations. Let's have a look at some further types of optimizations that 1DNN can do out of the box. So for instance, in ResNet 50, you have highly bandwidth limited operations. So this is an example where bandwidth may be limited. So by fusing some computations, you can capitalize on better usage of your memory. So here is an example where 1DNN will do a fused computation. So you have the convolution and then the convolution, ReLU, and sum in one step. So this is one way where it's capitalizing on memory. Graph optimizations, fusion is one example. Here, convolution 2D is being fused with bias. So this is done in one step, and this is one example. 1DNN will do this out of the box without you doing anything. Another example is layout propagation. So when we I would say when we convert this convolution 2D into the 1DNN version, so the name will be mklconv 2D, you need to convert this layout into this 1DNN world. So this will run much faster than this guy, and mkReLU will run much faster than this guy, but you're doing layer conversions at each step. So you can propagate this layout and have everything that's 1DNN related run into this its own world without doing the inner conversions here. So this also saves on convert overheads, let's put it this way. So on one hand, better performance with a mathematical operator and a saving on layout propagations. Now, memory, I mentioned that earlier. Using good optimized memory is key, is really important. So you may have seen a case like this where you're doing strided accesses on your memory data, which is really bad because you're having a lot of cache misses. Here's an example where you have a stupid loop like that, quote unquote stupid, right? So you have strided access. That's really not good. So having an optimized memory layout, for instance, for CPUs, having NCHW as a memory layout is very good. This means that your data is close in memory. So this is what we call data locality. So the data locality is optimized. Therefore, you have minimal cache misses. Now, you can even optimize on this data locality. One example is having blocked layout. So here an example, you're blocking 16 channels, and then you have like a block of 16 very close to each other. So then when you're working with your data, it's all in memory. You don't have to go and fetch it in DRAM. It's already in the cache, as an example. So now this is kind of theory, but 1DNN does that out of the box for you. So you don't have to go and tweak your code and find this and do this fine tuning. The performance library is doing this out of the box for you. Now, finally, system optimizations like load balancing, maximizing on the number of cores, maximizing on threading. So this as well, you could do this manually by playing around with those TensorFlow methods, inter-operations parallelism threads, intra-op parallelism threads. You could set this out manually, or you can just let oneDNN do this automatically. So right now, oneDNN is quite optimal and does this optimally for you. Let's have a look now. How does oneDNN interact with the frameworks, right? This is your typical code. I think this will be very interesting just for you to understand how oneDNN is used. And I said that oneDNN has this open API and it's backed by the CASTIEL standard, right? So we'll see how all of this is plugging together in this whole story. TF model, that's your Python code, right? You have load data, matrix multiplication, and then matrix multiplication with a post of like method post tanh, and then you're printing results. So here, these are mathematical related stuff. This is what oneDNN likes. It likes math, right? So in TensorFlow, the graph optimizer will eventually print out this piece of code. Now, here, look at how this matmul is being kind of replaced by the oneDNN version of it. So this piece of code will be this one here, where the load data remains the same. There's minimal oneDNN intervention here, but matrix multiplication will be the oneDNN version. GC is a gluing, it's glue, the glue code, right? oneDNN glue code, matrix multiplication, the same for these two, and then printing the result. Now, when this code is called here, we are here, it's going to call the oneDNN primitive for matmul. So this, you can see here, it's SQL code. Now, SQL code is great because this means that it can easily run on CPU or GPU. So this means that this piece of code that you had up there, you don't need to care, you don't need to do manual changes to run this on CPU or GPU. All of this is done for you by oneDNN under the hood, right? Now, to put some more clarity, let's have a look at the oneDNN architecture. This is very interesting. So first of all, oneDNN is open source, right? So when you have this SQL code of matmul, for instance, you are here. You have this DPC++ API. So it's going to check, okay, where do I have to run? On CPU or GPU? Let's say if it is GPU, then the dispatcher will then, one after the other, execute the optimized kernel for GPU. For instance, the optimized matmul kernel that runs very well on GPU. And then send it to the GPU runtime, aka level 0, right? So this is a path. And if it is CPU, then it's going to load the CPU optimized matmul kernel and then eventually run this on CPU. So this simple flow is done off the shelf, is just checking what hardware you have and choosing the best path to run the code on the best hardware. So this is done seamlessly, and it eventually makes your life easy. Now, the story with PyTorch is the same. In PyTorch, we have typically the A10 operations. So the A10 operations will be boosted by oneDNN. Now, the good thing is Intel already upstreams its optimizations in PyTorch already. So when you download PyTorch, you already have the Intel optimizations there. As we speak for TensorFlow 2.5.0, this is already done, but you manually need to set a variable like oneDNN enable equal 1. You have to export this variable, then oneDNN is activated. In the future, as from TensorFlow 2.7.0, this will not be the case. So you don't need to use this environment variable at all. You have it running with oneDNN enable by default. PyTorch is oneDNN is already enabled by default, but Intel is always, very active, very aggressive, wants to do things, ahead of time. For this reason, we have the Intel extension for PyTorch, aka IPEX. IPEX comes on top of PyTorch, and what it's promising is giving you early access to some aggressive optimizations, to some mathematical kernels. And to use IPEX, there's also here a very minimal code changes that you need to do to make the most of IPEX. Now let's have a look at this architecture of this whole story here. So how does PyTorch and IPEX fit in? So in PyTorch, we already have the CPU optimizations upstream. So the color coding is yellow for operators, blue for graph, and runtime optimizations in red. And in IPEX, what we have is more aggressive CPU optimizations on one hand. These will come from the custom kernels and the GPU optimizations. So if you currently have, let's say, an NDA version of our GPU, or somehow you have an early access, let's say on the dev cloud, there you would want to use the IPEX and then run a piece of code to run it on a little discrete GPU. So these are in IPEX. Now, like I said earlier, IPEX is here to provide an early taste of some optimizations. Eventually, the features of IPEX will find its path into the open source PyTorch version. Sometimes it takes time, and our customers, people don't have time to wait, and they want the optimizations quickly. So then they use IPEX, and we have like everything already in IPEX. With time, slowly by little, we upstream the optimizations, and when PyTorch people approve them, then it's integrated in the mainline. So even for IPEX, I have a small demo, and I will go very briefly through it, just to show you a taste of it. So this is also a very simple piece of code. It's just loading some data, some random data, and the model is ResNet 50, and then all I'm doing is an evaluation on this model, right? That's a very simple piece of code, okay? And I'm conducting actually 3 categories of tests. One will be done within PyTorch, and the second for each of the 3 experiments, I'm going to also run it natively. Natively here means using Torch script, which does jitting just in time. So it's basically leaving the Python world and running it kind of natively, just like C++ code, which is kind of it gives you better performance usually. So let's see how IPEX gives us better performance across the board. So I run the code without IPEX and in PyTorch. That simple piece of code here is just measuring the time and calling the data on the model, right? It took 9.8 seconds. And running this piece of code natively, it was supposed to be faster, but okay, I got 10 seconds. It's almost the same time. Now, what about using IPEX in the Python world? Doing the same thing with IPEX in Python. I do this is the same piece of code as above, and the time dropped from 9.8 seconds to 5.8 seconds. So here, IPEX did the optimizations more aggressively, giving me better performance. Now, the key thing is minimal code change, right? And this is basically the only thing that you would do. You import the library, import it extension for PyTorch, and then call IPEX.optimize. That's it, done. And the code gives you better performance. Great. Now, running that code natively, even better performance. So from 5.8 to 2.19. Now, I did run this on a Sapphire Rapids machine, which is not yet out, but I had access to it. And so doing that in bfloat 16 as well. So IPEX has support for bfloat 16. All you have to do is do something like that, like net IPEX.optimize and data type torch bfloat 16. So you're doing the same thing, 2.19, 2.2. So from 9.8 to 2.2, which is quite nice. So plotting all of this in the graph, this is what we have. Lower is better here. So the timing without IPEX in PyTorch and with IPEX with Apex in PyTorch, we are getting almost 2x performance boost. And if you do this in bfloat16, even better performance. So this is here leveraging a better data type for AI, let's put it this way, better performance. All right. Okay, so that being said, a brief look at the Apex architecture. You will have this in the slide, but I will just briefly say the blue parts are what Apex is providing, and the non-blue is what's already there. So the custom kernels are those aggressive optimizations provided by Apex. Performance is better across the board. You've seen some. So this is comparing FP32 performance. With Apex, we're getting better performance across the board for various AI models. And this is on a Sapphire Rapids that support also bfloat16. We get better performance with Apex. Now, with bfloat16, compared to FP32, the speed up is also better. So this is a value proposition here to leverage bfloat16 hardware. That will be Sapphire Rapids and upcoming discrete GPUs from Intel and Apex. If that feature is not yet upstream in stock PyTorch, right? So bfloat16 gives speedups of 1.5x plus across the board. That's for training, and same story for inferencing, speedup of 1.4x plus. So that's a value proposition right there. I think I have 5 minutes, but I know we have a Q&A after that, which we can use for generic Q&A. I will finish this presentation with 2 to 3 minutes, wrapping up with distributed deep learning with oneCCL. So oneCCL, this is short for Collective Communications Library, also highly optimized library from Intel. And it runs on basically anything, any kind of hardware you may be familiar. Rocket, Ethernet, OmniPath, scaling on CPUs, scaling on GPUs. So oneCCL seamlessly works on all of these. Now, the key thing in AI, maybe you've come across Horovod, right? And I would like to use a use case, in a real world use case, to show you how using Horovod and oneCCL and scaling on multiple nodes gave us better performance, training a really huge neural network with really huge data. So this is something that I've done with a customer 1.5 years ago. So they had a problem where they wanted to do segmentation on cancer, on medical images, right? CT scans. And they wanted an AI to look at it and segment areas of cancer. So that's the problem statement. We worked together with them and developed a solution for tumor segmentation. So they had huge, like terabytes of data. So we trained that neural network, and then on premise, like let's say at the hospital, you would use that trained model and do inferencing to get the cancer zones, right? But even that part here, the training, took a huge amount of time. Here are some examples like the customer was happy to share with us and that we can also share. So when we use one machine and stock TensorFlow, that training took 76 hours using one node. So first of all, we switched to using the TensorFlow with one DNN underneath, and we capitalized on performance close to 2x. So it took 43 hours without code change. And then we started looking at scaling out using multiple nodes. Here's an example where we used 2 workers, so leveraging the 2 sockets on the machine. We got better performance. So one DNN plus Horovod scaling on 2 nodes gave 2x from that line here to 24 hours. And then we scale on 4 nodes. And so the whole training time dropped from 76 hours initially on 1 worker, 1 node, to 16 workers and 4 machines. So that was huge performance boost using oneCCL, Horovod, which is a third-party framework here, and one DNN. So big value proposition to use optimized software and cleverly choosing your hardware as well. Now, I will finalize my talk with that very first slide you saw today. You guys are probably up here, but you're most welcome to looking into the performance libraries that are open source. And we have looked at optimizations for TensorFlow. We have looked at optimizations for PyTorch, as well as the machine learning part like Modin, Pandas, and scikit-learn. So these components are part of the AI Analytics Toolkit. And there is so much to say. Using this toolkit will make your life better because you're going to run your stuff faster, you're going to save time, you are going to be less stressed. So that being said, thank you for listening. If you have any questions, that is the time.